Hello, I am Monunath Beta, going to present myself on the laser physics. This is final project of this course. I chose the problem from the chapter 7, in which we have to find out the short lifetime of an in the population ratio less than the 1% for a 4-level laser. If we see the 4-level laser, there is the 4 different level with the different population, which is given by the NG, N1, N2 and N3. And here, and when the we give the pumping of a laser, and it giving a too fast decay near to the second level and the ground level, and there is a lasing action when the transition come across 2 to 1. So for this case we can write the rate equation for the N2 level and the N2 level, where the Rp is the pump rate and phi is number of the photon in the cavity mode, and capital B is the stimulated transition per photon per mode. Now, according to the question, when we here we can say that the lifetime of tau 1 is low for the lowercase level 1 is comparable for that with the tau 2. And we also can say that the lifetime of level 2 is purely radiative with the branching ratio of ratio beta for the transition from 2 to 1. Now, the upgraded equation of the rate equation at the level N2 and the N1 can be given by this. And when the laser is operated below the threshold level and within the steady state, so the phi 0 in the above equation here is 0. So by rearranging the term of that equation, we can say N1 oblique N2 is equal to the beta ratio of tau 1 and tau 2. And further, when we have to calculate the lifetime less than for the 1%, this equation is rearranged in the form of that. In the question, it is provided that the tau 2 is 230 microsecond and the beta is 0.51. So the short time period is come up to the tau 1 should be less than 4.51 microseconds. Now, from the chapter 8, I took the problem where we have to drive the output energy and the pulse duration which apply for a Q switched 3-level lasers. First of all, when we try to understand what is Q switching, the Q switching is a method for generating intense short pulse of light with the help of a laser. Let us consider there is a gain medium, and when we give the energy from outside with the help of laser, the gain is increasing, and there the feedback or the resonator loss is very high. At a time when the resonator loss fall at a point very sharply and the gain is high, in the result we have a output short pulse with a high power. We also called it giant pulse. So now to derive the equation, let us consider the population inversion is NT with the difference of the population at the level of N2 and N1, and phi t is the cavity photon number in the lasing mode. In the Q switching, this N and phi modified in the form of this equation, where B is again the stimulated transition rate per photon per mode, and tau c is represented for the cavity photon lifetime. Va is the volume of the mode in the cavity medium. The output energy can be given with the E is equal to, with the integration of 0 to infinite time Pt. Pt is the output power, and according to the it is same according to the for the photoluminescence with the, by taking the help of the equations for the photoluminescence, we can write this. So by using the boundary condition where phi 0 is phi 0 and phi infinity is phi final at is the 0, so the integration is come up to this, and the final expression can be written in the form of this, where Ni is the before Q switching and Nf is the after Q switching population. Now the pulse duration is defined in the defined like delta tau p, E oblique p. The subscript p is represent that the power is the peak power of the pulse, and the peak power of the pulse is given by this expression. As we know, the typical critical population is given by the NP is 1 oblique VA B tau C, and the reciprocal of the tau C is given by this expression. So when we arrange this term, the final equation come up to this point. So this one is the final expression which we are looking to derive the time period, and this is the energy of the pulse. Thank you.